Okay, I think that's going to work. Okay, it's going to capture my whole screen. All right. Okay, we're going to start here. Chemistry, the study of change for chapter 1. Okay, so you guys have chosen to study chemistry. Congratulations. It's fun, but it's a bit rigorous, or it can be. Okay, what I found. I love chemistry, so it's no longer rigorous for me. But probably for you guys that really haven't studied it yet, or others of you that have taken my earlier classes, that's good. That's smart. I like that. Then you should do well. Okay. A science for the 21st century is a lot of you are probably going to go to dental school, medical school, pharmacy, some sort of professional school, or even maybe a PhD in chemistry or a master's in chemistry or something like that. Okay. So there's a kind of feeds into a lot of different areas. Chemistry does within the professions and science. Okay. So you can do a lot of kind of inorganic chemistry kind of stuff with polymers and ceramics, or more of the organic stuff with food and agriculture. Okay. And here we see a nail rusting. That's what we see. That's the macroscopic kind of view of what we perceive. But what we don't see is kind of the microscopic view of the chemistry of what actually the molecules are doing. And that's what we're going to try to understand. We're going to try to understand them on that microscopic level of what these molecules, the oxygens and the irons, are doing when they combine to form iron 3 oxide here, which is rust. Okay, and how that process works and why it works. Why is iron going to react with oxygen? And kind of the ideas behind that. Okay, we're not going to spend a lot of time on the scientific method. We're not going to use it a lot in this class. That's more if you're doing actual research, which we won't be doing. Then obviously you would try to follow the scientific method for that. Okay, so how do we define chemistry? Okay, so chemistry is defined as the study of matter and the changes that matter is going to undergo. So that's how we would define it. You're studying matter and its changes. So, well, that begs the question, well, what is matter then? So we have to define matter to really understand this concept of what is chemistry. And matter is basically anything that occupies space and has mass. So if it occupies space and it has mass, then it's matter. That means basically everything that we see around us, that we can perceive around us, is matter. Even the stuff that we can't perceive. The molecules in the air, we can't see them. But are they matter? Absolutely. Do they take up space? Yeah. Do they have mass? Yes. Well, then why do they float? Because their density is less than our density, right? So maybe they don't really float. They're just less dense than us, so we sink within it. Water doesn't float, but we would sink in the water, right? But water is more dense than the air, so water falls farther or sinks within the air. So air doesn't really float. It's just has a lower density. Okay? So does it have mass? Yes, it has mass. Can we calculate the mass of air? Yeah, we could. Okay? It's made up of molecules. It's matter. Okay? So matter is classified in these ways. It's either a mixture or it is a substance. So if it is a mixture, then it breaks down into 2 other categories: homogeneous mixture and a heterogeneous mixture. And if it is a substance, it breaks down into 2 categories: either a compound or an element. So let's see. Here we see different substances. So the substance is matter that has definite composition and distinct properties. Okay? So here we have liquid nitrogen, which is very different than the solid gold. Okay? The gold is very different than the silicon crystals. They have different properties. They have distinct properties. So they are different things, so we would classify them based on their characteristics and so forth. Okay? And that's kind of where the periodic table helps us a little bit. It classifies elements. But once we get into compounds, then we have to look at the compounds distinctly, what their properties are. So, mixtures. A mixture is a combination of two or more substances. So we said a substance were these things that have distinct properties. And what happens when you have a mixture of substances? Well, those things are going to come together, but they are not going to really interact with one another. They're not going to combine chemically. They're just going to be mixed physically. Okay? So if it is a homogeneous mixture, that means the mixture is the same throughout the entire thing. So if I take a sample at the bottom of that mixture and a sample at the top of that mixture, it will have the same composition at the bottom as it does at the top. It won't be any different. And then we can classify it as homogeneous. But if we take a sample of the mixture at the top and at the bottom and they are different, then we would say they are heterogeneous. They are not uniform throughout. Heterogeneous. Okay? So homogeneous means, or homogeneous, means the same throughout. Heterogeneous means it is not uniform throughout the mixture. So here they're showing a few examples. Soft drinks, milk, solder. Those would be homogeneous mixtures. Salt dissolving in water. If I take salt and I put it in water, that salt will dissolve into the water. Do I have to do anything to make it dissolve? I don't. I could sit there and mix it, and that would increase the rate of dissolution, but it wouldn't affect the fact that it will dissolve anyways. Okay? It's going to dissolve anyways. But I didn't have to do anything. I could leave it there overnight, and the next morning I'd come back and it's completely dissolved. It looks like a clear solution. Well, the molecules have separated themselves. They have completely separated themselves throughout the entire mixture, or created a solution that is uniform throughout. That's how you can also know that this is a homogeneous mixture. The molecules are mixing themselves. I didn't have to do anything. They are mixing themselves. Soda. The molecules are mixing themselves. The sugar that's in the soda, the sugar dissolves into the soda, and those sugar molecules will separate themselves away from each other in exact proportions. Perfect. They will do it perfectly. So if I do the mixing, it's not going to be perfect. So if I sit here with this iron and this sand, and I sit there and I mix it and I mix it and I mix it and I mix it, can I guarantee that there's as many iron right here as there is in the middle? I'm never going to be perfect and guarantee that, right? I cannot mix it well enough by myself to guarantee that. So this will be heterogeneous. But if the molecules do it themselves, they're going to do a perfect job, and it will be homogeneous. And we'll call it a solution. It has created a solution. Solutions are homogeneous mixtures. They're clear. We can't see the particles because they have mixed themselves perfectly, and they're too small to see. Okay? All right. So now mixtures, a mixture means that they have not combined chemically. We've only taken those two substances and mixed them together. That means if we use physical means, we can separate them because they're not chemically bound. If something is chemically bound, you can only separate it through a chemical reaction. But because these things are physically mixed, then I can separate them using physical means. So you can see here that the iron can be separated from the sand with a magnet. That's a physical characteristic of iron. It's magnetic, so I can separate it. This sand is not magnetic, so they will separate by physical means. Okay? Here's another example. We have a distillation apparatus here. Distillation is the process of boiling and then cooling something to purify it. Well, why does that work? Because if I have a mixture of liquids and one of those liquids boils at a higher temperature than the other one, then the one that has the lower boiling point will boil first. And as it boils, it turns into a gas, right? And as a gas, it will travel up this distillation tube, and then it will collect in this collection tube here, where you cool it down with water that's surrounding the tube. You have water constantly circulating around the tube, and that condenses it from a gas to a liquid. And as it does that, you now collect it as a liquid. The other one is left here because it didn't reach its boiling point yet. And because it didn't reach its boiling point yet, excuse me, it stays here. And so you can separate those two liquids by physical means. Their physical boiling point allows them to be separated. Okay? Or even the salt water example. If I have salt dissolved into water and I boil it, the water will evaporate and what's left? The salt, right? So I have separated the water and the salt because the boiling point of the salt would be so ridiculously high that you would never even come close to causing that to boil away. Okay? The water would easily boil away. Excuse me. Okay, so what about an element? Oops, sorry. I better lock that. Jeez. Okay, so an element is a substance that cannot be broken into anything smaller. Okay, chemically. So obviously, these elements are atoms that are made up of different particles like protons and neutrons and electrons. That's not what we're talking about. We're saying we cannot chemically break it down into anything smaller. So these elements are the simplest units of matter, okay, which we call atoms. Well, it's a little outdated. 114 elements. They've actually just discovered these ones. So they've kind of have to update the periodic tables and things now. But so there's more than that now. 82 elements occur naturally on Earth: gold, aluminum, lead, oxygen, carbon, sulfur, some sulfur. Okay. 32 have been created by scientists, as well as those ones right there, because they don't occur naturally because they're radioactive and they just decay, so you can't really naturally produce them. Okay, so this would be the atomic symbol of the element by its name. That's how you identify it. So that's an element. Anything found here is an element. So if I have a piece of copper wire, I go to Home Depot and I buy some copper wire. It's an element. Okay, it's not a compound. It's a pure substance. It's pure copper. It's an element. If I purchase a piece of metal that's made of iron, it's what it is. It's iron. I go to the grocery store and I buy some aluminum foil. That's what it's made of. It's an element. Okay? It's an element. It forms metallic bonds with itself, and that's why it can. These metals are ductile and those sorts of things, but malleable, ductile, because of those metal bonds. But it's an element. Okay, it's a pure substance. It's a pure element. Now, compound is a substance composed of atoms of two or more elements, and they're chemically bounded in exact ratios, exact proportions. Okay, so if you have aluminum plus oxygen, those two things react. They have to come together in an exact way. And we'll talk about how we know how they come together in that ratio later, but that would be the ratio that they would come together in. It wouldn't be Al1O2 or anything like that. This is how they come together. We need 2 Als, 3 Os. Okay? That would be how they would bond with one another in exact proportions. Okay? So, for example, H2 plus O2. It's going to come together. H2O. That's the ratio that it comes together, right? Hydrogen plus oxygen react to form water in that ratio, H2O. That's the ratio that they'll come together in. Okay? So they need to be in those exact ratios. Okay. Which of the following is an example of a physical property? Oh, I've already given you the answer. There it is. Okay? So corrosive, if you see something say corrosive, that means it's chemically being corroded. Okay? It's a compound that's breaking down, and that it can only do that through chemical means. So iron breaking down into rust, okay? That's a chemical means that's happening, okay? If something is toxic, that means it's reacting chemically in your body to kill you, okay? Which isn't fun. Lead becomes liquid. That would be a physical means. So if I had lead solid, and it becomes lead liquid, I didn't change what it was, right? It's still lead. Lead solid to lead liquid. It didn't change its character. It didn't change what it was. It's still lead. It's just in a different physical state. It's no longer a solid. It is now a liquid. Okay? If I kept going, do the same thing. Lead, gas. It's still lead. It is now just a vapor, lead vapor. Okay? It is a gas. If you reach high enough temperatures, it would do that, right? It would go through all 3 states of matter. Those are the 3 states of matter: solid, liquid, gas. Okay? And everything can go through those states. Everything can become a solid, liquid, or gas. It just depends on the temperature and the pressure that you're either heating or cooling that substance at. That's what will cause it to enter those phases. Okay? Neutralizing stomach acid. That's going to be a chemical means, neutralization. An acid plus a base is forming water. That's a neutralization process. Okay. Flammability. If something is flammable, that means it's reacting with what in the air? Oxygen. That means it's reacting with oxygen. So if I take magnesium plus O2, oxygen, if you've ever seen magnesium burn, it's a very brilliant light, very bright. And you light it, and it just, well, fireworks, they use magnesium in fireworks a lot of times because it's so bright. But it reacts with the oxygen in the air, and it forms magnesium oxide. Okay? In those exact proportions. 1 magnesium, 1 oxygen. Okay? So, but that's flammability. So whenever I'm combusting something with oxygen in the air, okay, that's a chemical process. Okay, so these are all properties of tin. Which one is a chemical property? So tin can be hammered into a thin sheet. That's physical because it's a metal and it's malleable. That's what they say. So metals, the metal bonds, they have flexibility in them. You can move them, and so that's why we can hammer sheets of metal and make them thinner, or it's malleable. You can shape metal. Okay. At -4 degrees Celsius, a sheet of tin crumbles to a gray powder. Okay, so you can crumble it, but that would be a physical process. Tin, if it said it corrodes, that would be different, but it's not. It's saying it just kind of goes into a powder state. Tin metals are 231.9 degrees Celsius. Tin melts at 231.9 degrees Celsius. Okay, that would be physical. When a bar of tin is bent, it emits an audible cry. Okay, that would be physical. Okay, it erodes. There's the word, erodes. That's indicating that it's chemical, right? That's a chemical process. So we need to be able to identify when something is a chemical difference or a physical property. And that is simply by understanding that when we have something that is physical, it just simply changes its physical state. Solid, liquid, gas. Those are the 3 states, right? Solid, liquid, gas. So if it's going through those phases, that's a physical change. It's not changing chemically. But if it's changing its chemical composition, it is becoming something different. Okay? H2O, solid. Okay? This would be a what type of change? Physical change. It is not, it's still water even when it's a gas, right? Still water molecules, 2 hydrogens and 1 oxygen bound together as a gas. Okay, there's water vapor in this room. There's plenty of it out there. It's very humid, right? So, but it's just water. And if we cool it, it condenses. It'll condense, okay? But if I go from okay, if I do that, that's what type of change? Chemical, because it's no longer water, right? Is it still water? No, it's not water. It has become something different. It has gone from water to hydrogen and oxygen. Once that happens, that is a chemical change. Chemical changes change your identity. They change what you are. Okay? And that's how I'll be able to identify if it's a physical or a chemical change. If it retains its identity, that's just a physical change. But if it changes its identity by eroding with hydrochloric acid or something, then it's going to be a chemical change. That's a chemical change. Okay, so here's kind of an idea of those three states of matter. We have a solid. And you can see in the solid state, you're in fixed positions. The molecules, they're not moving around. They're fixed. They are moving around. They're just not moving over each other. Okay? So even the molecules in this table right here, it's a solid piece of matter. Those molecules are vibrating. They're just not rolling over each other like it would in a liquid. In the liquid phase, those molecules are rolling like this on each other. Okay? But in the solid phase, they're stuck, but they're vibrating. How could I stop them from vibrating? Well, in the solid phase, you're frozen. So let's talk about ice, water, ice. Those molecules are vibrating in the ice. How do I stop them? You're on the right track. Even though they're frozen.
Absolute zero.
Yeah, that's how I do it. You have to reach the coldest temperature, absolute zero, in order for all energy to be extracted from those molecules so that they will stop vibrating. And once that happens, you've reached absolute zero temperature. Kelvin temperature. Okay? So, water freezes at 0 degrees Celsius. So if I go below that, that's not absolute zero. Okay? Absolute zero is, so in Kelvin temperature, 0 degrees Celsius is 273 Kelvin. I would have to get to negative 273 degrees Celsius to reach absolute zero. Okay, so negative 273 degrees lower than the freezing point of water to reach that temperature of absolute zero. All right?
Does every element have a different absolute zero?
No.
It's absolute zero.
Absolute zero for everything. Okay, there's only one absolute zero where there is no more energy for those molecules to vibrate or move through Brownian motion, they call it. Okay, so once you reach that state, all motion would stop. But right here, they're still vibrating. You add some more energy, and they start to separate, and they start to roll. So when you think about chemical interactions, molecules interacting with one another, as you add energy, what happens to those interactions? They become weaker. Okay? Because look here. Those interactions are stronger, right? This is colder temperatures. They're stronger. They're holding on to each other. But as I add energy, what's happening to those molecules? They're beginning to want to gain their own identity. They want to separate away from the other ones because they're gaining energy and they want to, they're vibrating more, and so they're pulling away from each other. And here they're rolling over each other instead of being stuck together. Now they're rolling. I increase the temperature even more, and now they're completely separated. They're not even touching each other anymore. Sure, they might collide with one another, but they're not going to stay together. And that's when I enter that gas phase. Here's my gas phase. My molecules have completely separated, and they're just bouncing all over the place. So all the gases in this room, they're just bouncing everywhere right now. There's lots of matter that's just bouncing around us in this room. Okay? And so that's what's happening to my interactions. And that's the same with chemical bonds. The colder the temperature, the stronger those chemical bonds. The higher the temperature, those bonds begin to weaken. And at high enough temperatures, they would actually break. Okay? And a lot of times you will use heat to cause something to decompose or to break. Okay? Okay, so here different types of changes. We have a physical change. Does not alter the composition or identity of the substance. A chemical change alters the composition or identity. Okay? Hydrogen burns in air which contains oxygen to form water. Okay? So here you have oxygen and hydrogen, they combine to form water. Okay? That's a chemical change. All right, and we talked about matter occupying space. It has mass. Well, let's define mass a little more, because that's part of our definition, right? So we define chemistry as the changes that matter undergoes. So we have to define matter. And then as we define matter, we say matter is anything that occupies space and has mass. Well, now we need to define mass so we can truly understand, well, what is mass? Mass is a measure of your matter. And we understand that to be our weight, right? So I weigh so much. I know you guys wanted me to say it. But that would tell you how much matter is inside of me if I told you how much I weighed, right? It would give you an idea of the amount of matter that is inside of me. But the problem is that weight is relative. Matter is not, or mass is not. The amount of matter inside of me does not change whether I'm here on Earth or on the moon. But does my weight change from here to the moon? Yeah, because of gravity, right? So my matter is being pulled by gravity on my scale when I step on it, and it tells me how much I weigh. But if I go to the moon, there's not as much gravity to pull on my matter, so it gives me a different amount of weight. But my mass has not changed, right? My mass has not changed. So what do? Well, I have to standardize mass. So the international standards, okay, have been created so that they have taken, I don't know, it's like a piece of gold and made exactly 1 gram. They say this weighs exactly 1 gram. Okay? And so we can standardize our scales here on Earth to be that 1 gram. Then when I go to the moon, I take that thing which doesn't change its matter to the moon, and I can standardize the scales on the moon to be 1 gram for that amount. Then I would weigh the same here on Earth as I would on the moon. Okay? Because we have standards that have exactly 1 gram of matter inside of them. Okay? And that's how we would standardize mass. So yes, we can go to our scale and we can weigh something to be 5.69 grams, and we understand it to be that much matter. Okay? So it's okay. Okay? It's just not it's just that scale wouldn't work on the moon unless we standardized it too. Okay, which we could do, but that's the idea behind it. Okay, and we also have a system of units, which is not a U.S. system of units, because the U.S. system of units is a mess. And everywhere else in the world, they use the metric system, which makes sense. So we haven't quite figured that out, but that's okay. We have a foot and a pint and a quart, and okay, that don't relate to each other very well, except through really complicated means. Okay, or you could do a very nice metric system, which science does, because it's it's a beautiful system. Okay, length is the meter, mass is the kilogram, time is the second, electrical current, the ampere, temperature Kelvin, amount of substance is a mole. Luminous intensity is the candela. Okay, so it doesn't. These all could be different things that describe what you're measuring. I'm measuring the length of something, so it's in the meter. And these would be the symbols here for those. Okay, but I can easily change that meter to be 1,000 times it and make it a kilometer. Okay? Or 1,000 less than it and make it a millimeter. But it all relates back to that base amount, that base unit of the meter, the kilogram, the second, the ampere. Well, here would be, I guess, the gram. But the amount that we measure things in science would be a lot of times in the kilogram. But the base unit would be the gram, right? The second, I can make it milliseconds, kiloseconds, okay? I can easily change it to those. That's why this system works so well. Okay, so here we see some of those prefixes. We call them the prefix. So the letter you put in front of that base unit will tell you how much it's changed by. Okay? So, kilo, mega, giga, tera, excuse me. You guys are probably familiar with those because that's what our computers use, right? For bytes. Kilobytes, megabytes, gigabytes, terabytes, okay? And, these days we're all the way up in here. And, whereas, just a few years ago, this was amazing. We're like, man, I have this many kilobytes in my computer. That's amazing. Yeah, you guys are too young for that, right? So, but yeah, that's how it used to be. Okay? You're going to use liter a lot, which is the measure of volume, the liter. And you're going to use milliliters and liters a lot. So a liter, 1,000 milliliters equals 1 liter. Okay? And that is what this is attempting to show you. Okay? The milli is 1/1000th of a liter. Or, in other words, 10 to the negative 3. So if I write it in scientific notation, 1 times 10 to the negative 3 liters equals 1 milliliter. Okay? Do you see why this is starting to get confusing? Because we kind of perceive it like this a lot of times. 1,000 milliliters is 1 liter, but then they're telling us 0.001 liters equals 1 milliliter. It all means the same thing. You just have to get it straight in your head because you're going to have to use these conversions a lot of times when we're answering questions. Because you might be given units of milliliters and your answer needs to be calculated in liters. And you're going to have to convert it. All right, we're out of time. Time goes by fast. Okay.